Continuing to unpack this expression of attenuation constant alpha, let's look at the case where we have a metal. What is the case where we have a metal? Well, we know in a metal that the conductivity is going to be very high. In that case, the attenuation constant, which is this expression up here, let's look at it down here, it's going to be omega times mu epsilon over 2. If you look at what's going on inside here in this expression, you see that the sigma, the delta over omega times epsilon is going to overwhelm that one term. So that's going to be, and then you take the square root of it, so it's going to be roughly the conductivity over omega times epsilon. And there would be a -1 term here, but that's basically a lot smaller than what's going on over here. So the simplified assumption is this is equal to omega times mu epsilon over 2. Got this. Okay, let's move on down. Let's bring the frequency to the inside. Omega squared over 2. This, I'm going to write in a different color. This cancels out with this. This cancels out with one of the exponents. And what we're left with is the absorption coefficient is roughly equal to omega mu conductivity over 2. Let me just check and make sure I did that right. And I did, in fact. What this is often expressed as 1 over delta, where delta is the skin depth. Now, we made this assumption where we're talking about a metal here. So when you hear the term skin depth, and when you see equations about skin depth, that only applies to metals. It doesn't apply to lossless dielectrics, and it doesn't apply to lossy dielectrics. Incidentally, I'm going to go on and do the calculation for a lossless dielectric and tell you what I mean by lossless dielectric. Okay, let me scroll down. I'm going to go back to white. Let's look at the case of free space for a lossless dielectric. Okay, let me write the generalized expression for the attenuation constant again. Alpha equals omega mu epsilon, I'm just going to write it out, over square root 1 plus over quantity squared minus 1. What do I mean by lossless dielectric? Or rather, what do I mean by, in turn, what do I mean by lossy dielectric? It all comes down to this term here, the conductivity, right there. If this term is very small, if it's essentially 0, then we're dealing with a lossless dielectric. So let me actually write this out. So lossless dielectric, electric is where the conductivity is approximately 0. Lossy dielectric, I can't write today, erase that. Lossy dielectric is where the conductivity is mid-value, and metal is where the conductivity is very high. That's what determines how you do this calculation, how you interpret the results. Let's go on and do this calculation for the case of a lossless dielectric. In the case of a lossless dielectric, that, as I just said, that sigma term, that conductivity term is about going to be equal to 0, so the characteristic impedance is approximately equal to omega times mu, this. What happens inside here is we have the square root of 1 minus 1. And what is that? That's 0. So for the case of a lossless dielectric, the attenuation constant is approximately equal to 0. What does that mean? That means as the electromagnetic wave travels in a material with this characteristic, with this attenuation constant, there will be no loss of the signal. There will be no attenuation. And this makes sense if you think about it. If this wasn't true, then the light emitted from stars that are light years away from us, light years that have a long distance to travel, if this was even very small, if it was 0.0001%, whatever, some very small number, that light wouldn't reach you, or some very small fraction of it would reach you, and yet the light reaches us. So the interstellar space is mostly a lossless dielectric. Great. I'm going to take a pause. Okay, I'm going to make a quick comment that the intermediate states where the conductivity is mid-range, you need to just calculate out this attenuation constant. Also, this absorption, what's going on with this energy from the electromagnetic wave gets absorbed in a material. Mostly it gets dissipated as heat. And I say mostly, actually I should say almost always it gets dissipated in heat. This is true for most materials. For semiconductors, something else can happen, which has to do with band gap energies and whatnot, but we're not going to talk about that here because definitely nothing within our system, the scalp, the skull, or the brain is a semiconductor material. We don't need to worry about that. So all the energy that gets absorbed is dissipated as heat. I'm going to take a moment here and clear my screen and go on. Now that I've defined characteristic impedance, defined absorption, depth, attenuation constant, let's look at a cartoon picture of a boundary. Here's the boundary. Two materials. Over here we have characteristic impedance Z1, and over here we have characteristic impedance Z2. This could be air, and this could be the scalp. Okay. What we have is the impinging electromagnetic wave, EI, and actually I should note from this point on I'm going to talk about you can talk about things in terms of electric portion and the magnetic portion of the wave, and they're related. I'm only going to deal with this portion because that's how I've done my calculation, and in some ways it's more intuitive to think about it. But this holds true for the whole thing. Okay, we have the impinging electromagnetic field, E sub I, the impinging electric field. Let me try to correct my terminology. There will be some amount that's transmitted, and that's going to be gamma sub T times E1. EI, rather, and there's going to be a reflected portion. That's going to be gamma sub R times EI. What are these gammas? Well, this gamma is the transmission coefficient, and this gamma is the reflection coefficient. If you go through, this can all be derived from Maxwell's equations, but it has been derived, so I'm just going to write it out. The reflection coefficient, I'll write that first over here, gamma sub R equals the minus going electromagnetic wave at that boundary over the plus going electromagnetic wave, EI. So it's going to be, you just do the math, that's what it is. And the expression for that and characteristic impedance is going to be the load impedance minus the first impedance, Z1, over Z1 plus Z2. That is what it is. And for the transmission coefficient, I'll just write it out. That comes out to be 2Z2 over Z1 plus Z2. And what relates these two quantities? Well, we can say that this is true. The the transmission coefficient equals the reflection coefficient plus 1. Okay. Let's look at a few cases, metal and non-metal, to see what would happen. In the case of a metal, we know that Z2, where the second I'm talking about, let's assume the first Z1 is for free space, so Z1 equals 377 ohms. And if it impinges upon a metal, so Z2 is much less than Z1. Let's say that. So going back up here to this image, I'm going to say, instead of this being the scalp, what if this was a metal? And we can say that this characteristic impedance is much less than this. That's the assumption I'm going to make. Okay. In that case, what do these expressions equal? Well, here's the reflection coefficient, and there's the transmission coefficient. Well, in that case, the reflection coefficient equals, let's say Z2 was approximately equal to 0. So much less than it's approximately equal to 0. So we have 0 minus Z1 over Z1 plus 0, which is minus Z1. I'm sorry, minus 1. And what is the transmission coefficient in this case? Well, it's going to be equal to 2 times 0 over Z1 plus 0, which is approximately equal to 0. Well, that's easy to understand, relatively. You can say for a metal, there's no transmission. 0. And that can make sense if you think about light impinging on a mirror, which is that light is an electromagnetic wave. None of it gets through, it all gets reflected. But what does it mean to say the reflection coefficient is minus 1? Well, that means all of it's reflected and there's a phase shift. That minus 1 means that there's a phase shift. I'm going to stop here and go on to the next video.